our third talk is by Xinchi from Fudan University, and their paper title is called Adversarial Multi-Criteria Learning for Chinese Word Segmentation.
Hi everyone, it is my great honor to share our work here. What we have done is about Chinese word segmentation. Different linguistic perspectives cause many different segmentation criteria. Most existing methods focus on improving the performance for each single criteria. However, it is interesting to exploit these different criteria and mining their common underlying knowledge. In this paper, we propose adversarial multi-criteria learning for CWS tasks by integrating shared knowledge from multiple heterogeneous segmentation criteria. So, first of all, I would like to talk about what the Chinese word segmentation is. As we know, Asian language do not have spaces between words like English, so we have to segment sentence into words first. As the example shows on the slide, Yao Ming reaches the final. We aim to find out the missing spaces. Why CWS tasks is important? Because Chinese word segmentation is the preliminary step for a bunch of Chinese natural language processing tasks such as parsing, text classification, and so on. Although it is said that we could directly use characters as input instead of words in the end-to-end framework, we could still observe significant improvement by using CWS technique in advance. For CWS task, word segmentation have multiple criteria. As the example shows here, given a sentence Yao Ming reaches the final, the two commonly used corporate PKU and CTB use different segmentation criteria. The question is how to exploit all the corpora with different criteria to improve the performance of each dataset. How to exploit these different criteria and mining their common underlying knowledge. And that is why we propose our model here. And in conventional neural models, CWS task is usually regarded as a character-based sequence labeling problem. Specifically, each character in a sentence is labeled as one of label set B, M, E, S, indicating the begin, middle, end of a word, or a word with a single character. Figure on this slide illustrate the general architecture of the CWS task. The general architecture of CWS task, it could be categorized by three specific components: an embedding layer and feature layers consist of several classical neural networks and a tag inference layer. The role of the feature layer here is to extract features, which could be neither convolutional neural network or recurrent neural network. In this paper, we adopt bidirectional LSTM followed by CRF as a tag inference layer. Specifically, the probability of the sequential prediction Y of a given input X could be formalized as this equation, where psi here is a global feature which could be derived by some local features, and the score in this function could be is the output of the neural network here. For instance, this S is somewhat the output of that neural network. So now I would like to start to introduce our model. Formally, assume that there are M corpora with heterogeneous segmentation criteria. We refer DM here as the corpus M with NM samples, and where XMI and YMI denotes the I sentence and the corresponding label in corpus M. And to exploit the shared information between these different criteria, we propose 3 sharing models for CWS task, as shown in this figure. The feature layer of these 3 models consists of a private LSTM layer and a shared LSTM layer. The components here are folded. I mean, XA, XB indicates the sentences coming from different data sets with different segmentation criteria. The yellow rectangle here indicates a shared LSTM layer, and the green one is a private LSTM layer. The difference between these 3 models is information flow between the private layer and the shared layer. Besides, all of these 3 models share the embedding layer. Under the setting of our model, our objective function for segmentation task is to maximize the likelihood of these M data sets. As shown in these slides, we sum up all the instances in M data set, and XIM and YIM is mentioned above. And theta M and theta S indicates a private parameter set and shared parameter set, respectively. The theta M and theta S. Furthermore, we introduced the adversarial training strategy on multi-criteria learning for CWS task. Although the shared private model separates the feature space into shared and private spaces, there's no guarantee that the shareable features do not exist in private feature space. Therefore, we jointly optimize the shared layer via adversarial training strategy. Besides the task loss for CWS, we additionally introduce adversarial training loss to prevent criterion-specific features from creeping into the shared space. So what's the definition of adversarial training strategy here? Concretely, we will introduce a criteria discriminator. We introduce a criteria discriminator which aims to tell which corpus the sentence comes from, according to the features extracted by the shared layer. And the shared private model aims to fool the discriminator so that we could prevent the criteria-specific features from creeping into the shared space. And the objective function of adversarial training consists of 2 main components, the discriminator loss and the entropy loss. They are adversaries. The theta d is the parameter set of the discriminator, and the theta s is the parameter set of the shared layer. The training process will iteratively optimize these 2 parts. Specifically, when training on discriminator, we only optimize theta d and fix the shared parameter theta s, while when we train on shared primate model, we only optimize on theta s with theta d fixed. Unlike previous work, which used the inverse gradient of discriminator as adversarial training strategy, we use entropy loss here instead. Experimental results show the effects on the convergence speed by using the entropy loss here. The total loss consists of these 3 parts: the segmentation loss, the discriminator loss, and the entropy loss. For experiment. To evaluate our proposed architecture, we experiment on 8 prevalent CWS datasets from Xipeng 2005 and Xipeng 2008. Among them, AS and CKIPCITYU are traditional Chinese, while the remains are all simplified Chinese. In this paper, in order to use the same embedding table, we map traditional characters to the simplified form. Table on this slide shows the experimental results of the proposed models on test sets of 8 CWS datasets, which has 3 blocks. For simplicity, we only list the F values here, and we could mainly focus on the result listed on the last column, which are average F-scores on 8 datasets. The first block shows the baseline results. BLSTM is a model with one BLSTM layer in the feature layer, and the stacked BLSTM layer is a model with two LSTM layers stacked. And we could observe that the performance of BLSTM cannot be improved by merely increasing the depth of the network. In the second block, our proposed three models based on multi-criteria learning boost the performance. Compared to the baseline result, the proposed model boost the performance with the help of exploiting information across these heterogeneous segmentation criteria. Although various criteria have different segmentation granularities, there are still some underlying information shared. And in the third block here, by introducing the adversarial training, the performance is further boosted. And the model 1 seems slightly better than model 2 and 3. However, the boost from the adversarial training strategy is not significant. Traditional Chinese and simplified Chinese are two similar languages with slightly different on character form. We investigate if the knowledge learned from the simplified Chinese could help to improve the performance on traditional Chinese. The table on these slides gives the result of model 1 on 3 traditional Chinese datasets under the help of 5 simplified Chinese datasets. Specifically, we firstly train the model on simplified Chinese dataset, then we train traditional Chinese dataset independently with shared parameters fixed. As we can see, the average performance is boosted, which indicates that shared features learned from simplified Chinese segmentation criteria can help to improve the performance on the traditional one. As AS dataset here is relatively large, the feature learned by the shared parameters might bias to other datasets that hurt the performance on such a large dataset AS. So in this paper, we propose 3 shared private models to integrate multiple segmentation criteria. An adversarial training strategy is used to force the shared layer to learn criteria invariant features. We conduct extensive experiments on 8 CWS copper with different segmentation criteria, which is by so far the largest number of datasets used simultaneously. And thank you for your attention. And our code is available at GitHub website. Thank you.
Many Chinese word segmentation experts sitting right here, so you guys must have questions. Please ask us some questions. Sujian, Xiaoqi, do you guys have questions? Can you come to the microphone? Because we're doing videotaping. Some people are doing videotaping.
Hi, really nice work. I have a small question. So you try to combine the different criterions, right, and into your training, but one small question is that, is it possible that improvement was caused by more training data? Because when you do this, at the same time, you use 8 different corpuses, right? So compared to, those one data set, so you have basically 8 data sets. So is it possible the improvement was caused by that?
Good question. And our purpose is to utilize the annotation from different criteria. That is our purpose. And the problem is we could not simply to concatenate all the data set together because for some corpus or some criteria, we just want to segment one word into 2, and for another, we just want to segment into 1 word. And if we put them all together, we will learn something mass. So that is our contribution to combine and not simply concatenate all the data set together and train a simple model here.
Okay, so you still use the single data set, but you just expand the...
Excuse me?
I mean, you still use the single data set for training, but you just expand the criterions and to allow the different variants, right?
In our model, we use some multitask learning framework to regard each criterion as a task. Yes, that is our model.
Okay, got it. Thank you.
Thank you.
Hi, great talk. And I have a question about the number you showed in your table. Are they accuracy, precision, recall, or F1 measure?
You mean the table here, right?
Right.
It is a F value, which is average of precision and the recall score.
I see. And how do you calculate this accuracy? Do you do binary classification, or do you do like
what do you mean by binary classification?
Because you are doing segmentation, right? So
yes.
But I also see 4 labels in your demo, like S, B, and.
Yes. Sorry for.
Yeah, there are 4 labels here. So do you do like binary classification at each position, or do you do 4 classes classification here?
Okay. Your question is about evaluation, right?
Right.
The evaluation in CWS task is common, and so I just neglect this part here, and I'm sorry for that. The CWS task is aimed to evaluate our result sentence by sentence. I mean, how many words have you segmented correctly, and the ratio is precision, and how many words have you predicted correctly is the recall, and we get the average, which called the F score, and there is the equation and a clear definition of that. It would be in my paper, and you could check it later. And for this framework, because Chinese word segmentation, we always regard this problem as a sequence labeling problem. So the label set here could be S, B, M, E. The label set with size is 4, and we could also use another labels. For instance, BI, and which indicates the beginning or the middle of a words. Then this I am Chinese. This sentence could be B, 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 I.
I see. Thanks.
Thanks very much.